Okay, everybody, today we're going to talk about the next part of the energy unit, and this is going to actually be heat. So we're going to take a little bit of a closer look at heat and how we calculate heat in this video. So grab yourself a pencil and make sure you have a calculator too, and be ready to go. Heat energy. What is it? What do we do? How do we measure it? Just to give you an idea here, let's take a scenario where we have some hot water in a box, in an insulated box here, with a thin metal wall in the middle of it. We have some cold water on the other side. Okay, and the mass of the water in here is about 10 milliliters or 10 grams in both sides. And the question I have is, what happens when they're in contact like this? So, do you actually? What happens as a result? Um, and that becomes the issue of what happens in terms of the energy transfer. Are we transferring energy from the hot water to the cold? Or are we going from the cold to the hot? And that's the big issue on heat flow. So, a really important thing to know is the direction of heat flow. All right. So, uh, really, the definition of heat, or one of the definitions, or a good definition of heat, is thermal energy, which arises from the movement of all the particles and the energy that's in the sample, uh, and that's energy that's going to flow, okay, from an area that has a high temperature to an area that has low temperature, okay, and that's the push. You always have heat flowing from high to low and not in reverse, okay, and that's really interesting and really important to remember that it doesn't flow opposite, okay. Things that are cold don't get colder, and things that get hotter by force. Okay, that happens. That would not happen unless you forced it to. So the natural flow of heat is always from where there's high to where there's low. Okay, so that's really important. Okay, to understand. And again, test questions or exam questions will always lead you in that direction. So it's important to know that. All right. Again, and this is going to continue to happen until no heat flows, and that you reach something called thermal equilibrium, which is really when um, the temperatures become equal. Okay, so once you become equal temperatures, no more heat will flow from the high area to the low area. So that we call it thermal equilibrium. So just keep a little guideline here. Okay, don't confuse temperature and heat. Okay, heat is not temperature, and temperature is not heat. That's an area of confusion sometimes. You got to be careful. So temperature is energy. I'm sorry, heat is energy that flows from high temp to low temp. So think of a high temp to low temp as the push. All right, so a little quiz here, a little practice question. Which statement describes a transfer of heat that occurs when ice cubes, and we know what ice cubes, temperature of ice cubes are, okay, are added to an insulated container containing 100 milliliters of water at 25. Okay, now that the amount of water here is not important, but we know that the ice cube will definitely be colder than the water, right? So heat would probably flow. We expect the heat to flow from the water to the ice cube. So the ice cube is going to gain energy and the water is going to lose energy. And you'd be in here at number three. Okay, so that's important to know that they both won't lose or both won't gain. One has to gain from the other. Okay. All right, so how do you actually measure heat? Okay, and measuring heat is going to be a really important part of this. This is used all over, not only to measure reactions that release or absorb heat for different purposes, but also in the food industry. Okay, so let's just say you had a bagel, and you had 300 calorie bagel, uh, and you were wondering what that really means. What does it mean to have calories in foods? Well, calories is really the heat or the energy that's given off once you metabolize or you burn the quote unquote burn the bagel in your body. So it's really heat that's given off. So it's the potential energy that's in there. Now, again, you can really measure heat as calories, which is the old way to do it, or joules, which is the current metric way to do it. So you could do it either way. In food science, we still use calories, but in other areas of science, we use joules. So there's still a bit of confusion on when to use what, but again, in science, in our classes, we're going to be using joules. Okay, so if a large bagel has that, what does that really mean? Okay, it means when you burn the bagel, you release that amount of heat. Okay, and that's how we know the calorie count is by actually burning food. In a food science lab, they put it in something called a calorimeter. So we'll look at that in a minute. So a couple of things. Heat, we're going to give it the symbol Q, lowercase q, is going to be measured in joules, okay, or calories, but we're going to use joules. So we'll use this more often. Okay, just a couple little things as far as the numbers go. Okay, if you have 1,000 joules following the metric system, you will have 1 kilojoule. Joule is a very small amount of energy, as is a calorie. So we generally don't use just joules. We generally use kilojoules or kilocalories when we use food. Okay, so just keep that in mind. If you do say kJ, that typically means kilojoules. All right, so what we normally do is put this. This is a simple calorimeter or a coffee cup calorimeter, where we fill this with water, and then what happens is you have a sample that's releasing, absorbing heat. Okay, and let's just say we use the example of releasing heat. The sample would release heat to the surrounding water. Okay, the water would gain that heat, and then we can measure the temperature change of the water as it goes from some low area to some higher area. Okay, no heat can get in from the outside because this is going to be insulated, and that simply means that heat can't go in or out of the sample. All right, but there always is some error in a calorimeter because the parts of the calorimeter themselves actually absorb heat also. So you're going to have always some error when you use a calorimeter. So again, a simple calorimeter measures heat. Okay, so it's important to know that a calorimeter is a heat measuring device. Okay, so just some common foods, calorie heat amounts. An Oreo cookie has about 100 calories in it. A gram of protein has 4 calories in it. Carbs also, and fat has higher calorie amounts, and that would be in 9 grams of fat, in 9 calories per gram in a gram of fat. And just to keep in mind, watch this little c versus big C. You'll see up here you have a small c. A big C is actually like 4 kilocalories. Okay, so that's really 4,000 calories. So you can just imagine what a Oreo cookie has when you think about the large C being a kilocalorie rather than a small calorie. So that's something interesting to talk about and ponder. Okay, so quickly, the calculation of heat energy. How do we actually calculate the amount of heat? Okay, we're going to use this little formula, and it really has 3 things in it. It has going to have a mass. So the amount of heat that you measure is dependent first on the mass. Okay, the change in temperature we talked about is important because a large temperature difference will have a large amount of heat transfer. Again, you're always going to go from high to low. So there's definitely a temperature change factor here. And then the specific heat is a value of what it's made of, like based on, what is the thing made of that's actually transmitting the heat, because different materials have different abilities to store or transfer heat from one place to another. So all of these are going to come together in this calculation. The units themselves, mass will be in grams, specific heat will be in joules per gram degrees Celsius. So the specific heat contains all of the units here. Okay, and then you have a change in temperature. So use your dimensional analysis, everybody. I know you love it. If you cross this with this and then grams with grams, you'll be left in joules, which is our final answer. So you like that. So that's another way you can actually do this. All right, so what does it boil down to? Basically, Q is going to be equal to the mass of the substance times C, and uppercase C is going to be the specific heat symbol. Okay, and the temperature here, the change in temperature, will be delta T. Okay, and again, delta means change. Okay, so don't forget that's change. So that's going to be the difference in temperature. Sometimes it's referred to as the temperature final minus the temperature initial, if you want to use it that way. Again, there's a few different ways you can do this. I'm going to choose one way. Again, different teachers may use different ways to do it, and that's fine. Okay, and again, that's what the delta T means. Okay, so that's how we do it. Let's do a quick example on actually how we do this. But a quick word on what specific heat is. Specific heat is simply the amount of heat needed to raise a certain amount of something by a Celsius degree. So, for example, if you had let's just say you had this little sample test tube of water, and you wanted to take that 1 gram of water and you wanted to raise that from, 13 degrees Celsius up to 14. Okay, so you put a little candle under that, you'd add some heat, okay, and if you did that, okay, that would be 4.18 joules. So it would take 4.18 joules to raise 1 gram of water a Celsius degree. And that's where we get that from. Okay, so again, the magic number for water for C is always going to be that number. So that's what you're going to have to, I want you to memorize that number. That number is going to be important. No, 4.18. And that's going to be for liquid water all the time. Okay? If you had, aluminum or you had silver, you could see they have lower specific heats because metals typically would have an easier transfer of heat. They need less energy to transfer their heat. Okay? Water has a very high heat capacity. Okay? It has very difficult time raising its temperature. You need a lot of heat to raise its temperature. Metals are just the opposite. So that's just a quick word on this thing here. All right. As far as measuring this, let's go over a quick problem on how we do this. And let's just say we have a problem of how much heat is needed to raise a certain temperature of 150 grams of water from 20 to 35. So let's draw a little quick picture. Okay. And let's just say we have some water in here, and there's 150 grams of water in here. Okay. And it's at 20 degrees Celsius, and we want to raise the temperature up to 35. So we definitely want to heat this. So we're going to add heat, and we want to know how much heat are we going to need to raise the temperature from some value to some value. Okay, so what you can do is you're going to use, again, you're calculating heat. You have a temperature change, so we're going to use this little formula. Okay, and I like to make just a quick little chart. So Q, M, C, delta T would work. You could do that way. All right, so it's asking you for how much heat. So that's going to be my X value. I have my mass here at 150 grams. That's easy. Okay, now the C is always going to be 4.18. So 4.18 joules per gram degree Celsius. Okay, and again, my difference, I like to keep the difference positive because it keeps my numbers positive in this case. So what I'm going to do is I'm going to take 35 minus 20. Okay, and I'm going to get 15 degrees Celsius. So this is my change in the temperature. I don't want the initial or the final. I'm looking for the change. So that kind of is easy, right? So I'm going to say Q equals my M, my C, my delta T, and I'm simply going to go 150 grams, okay, times my 4.18 joules per gram degree Celsius, okay, and then I'm going to take that times my 15 degrees. Okay? And if I add that together and look at this, grams cancel with grams, Celsius cancel with Celsius, I'm looking for my Q, and again, Q is going to equal, if I did this right, should be 9405 joules. Okay? I'm not going to pay attention to significant figures right now. I'm just going to leave it at that. So that would be a simple heat problem on what you do. Okay? So I can pause. You can give it a shot. You can write that down. Give it a shot for a minute. Okay, we're going to go over the next problem. The next problem is a little different. So what we could do is we could go and try that one. Let's see. Well, I'll do it down here. Let's do this. A little different. All right. So down here, I know it's hard to see through the writing here, but I'm going to go with it anyway. Okay. As far as the final temperature, let's just say this is a little different. So what's the final temperature of the water if 1,000 joules are added to 40 grams of water initially at 27? So I'm going to go over here and draw another beaker here, right? And let's just say now I have 40 grams of water, okay? And I got a thermometer in here, all right? And I'm starting at 27, okay? And I know I'm adding 1,000 joules to this. So that's going into that. So think of like a lighter or a heater, you're adding this. And let's just say I add a certain chunk of heat or a little amount of heat. Where does that temperature end up here? I mean, where is that going to go? So that's an interesting type of problem. And I like to phrase it this way. This is my way of doing it. And I think it's a little bit a different way to do it. So if you say, hey, Q equals MC delta T, what I'd like you to do is solve for delta T, right? So if we do that, we change our values, well, we'll get Q is going to be divided by MC, right, big C, and that will equal a delta T. So as long as we know our values, we're good. So let's just check over here. We got Q, We got M, we got C, we got delta T. Okay. Now Q we do know this time. We know it's 1,000, right? We know our mass is 40 grams, and we know the initial temperature, but we don't know the final, so we do not know delta T. So I'm going to make that X. Okay. And my C we know is 4.18 because it's liquid water. All right. So in this case, instead of worrying about a minus side, what I'm going to do is I'm just going to solve for X. So I have my formula here. Okay. So I'm going to put the values in. I have 1,000 joules. Okay. Divided by my mass times 4.18. Okay. And I'm going to get about approximately 5.98 Celsius. Okay. Which we'll say is about 6 Celsius. So that's fine. But that's not my final answer. Remember, they're looking for the final temperature. And you're starting at 27. That's your starting point. So your final temperature has to go up by that change. Right? Remember, this is the change in temperature. You just solve for the change in temperature. The change is 6. Now, because you're adding heat, we'd expect that temperature to be higher. So final answer, okay, is going to be the 27 degrees that I started with plus the 6 degrees, and I will be at 33 degrees Celsius. All right, so that's a little bit of a different take on this type of problem. Okay, so if you have to come back and look at it, that's fine. To repeat, if you're looking for the final temperature, solve for that solve for the change in, and then you can add it to the initial. Again, this is the starting temperature, right? This is the starting temperature here. Okay, so that's your first start at measuring heat when you have a temperature change. We'll come back at another day and we will look at how we monitor this for phase changes. Have a great day.